or until we finish the chapter, whatever comes first. Okay, so with that said, let me just get the Zoom feature just right, and let me switch to tablet mode so I can show you the molecular models that we'll need. Okay, we're in drawing mode. Okay, so we did some naming. Let's talk a little bit about stereochemistry of alkenes once again, just to review. So an occupied pi orbital, so carbon-carbon double bond involves both a sigma and a pi bond. And this pi bond, this full pi orbital, prevents rotation. You can't rotate double bonds. So as we discussed last chapter, a cis alkene has substituents on the same side of your alkene. A trans alkene has substituents on opposite sides of the alkene. So this would be cis 1,2 dichloroethene. This would be trans 1,2 dichloroethene. Okay. Now, as we've seen before, if there are multiple substituents on an alkene, we utilize Z and E assignments instead. So just as a refresher for Z and E notation, you rank each group on each side of the alkene in order of priority. If the highest priority groups are on the same side of the alkene, it's Z. If the highest priority groups are on the opposite side of the alkene, it's an E alkene. So as we see in this case, fluorine and oxygen are highest priority. They're on the same side, so this would be a Z alkene. Okay. In this second example, the fluorine and oxygen, which are our highest priority groups, are on opposite sides, so we would have an E alkene. For those who've been reading ahead or who are generally curious about organic chemistry and may have seen this motif before, does this structure ring a bell for anyone? Does this type of motif ring a bell for anyone? There's a special name for this type of special alkene. Just for those who are curious, this motif here is known as an enolate derivative. And you'll see these a lot in upper division organic and in Chem 113. Okay, so in terms of priority, once again, just as a refresher, the higher atomic number gets the higher priority. So for example, on the right-hand side, chlorine gets priority, and on the left-hand side, carbon gets priority. So since our substituents of highest priority are on opposite sides, this is the E alkene. In this example on the right, since our high priority groups are on the same side, we get a Z alkene. Just like before, if the atomic numbers are the same, you compare at the next connection point at the same distance. So you keep moving down the chain until you see a difference in priority. We've done this before. Remember, do not combine. You're not looking for the highest total priority. You're looking for the highest priority for each individual atom. And once there's a single difference in priority between your atoms, the highest priority atom wins out. Finally, just as a refresher, multiple bonded atoms are equivalent to the same number of single bonded atoms. So now what we're going to do is we're going to use this knowledge and we're going to try to assign E versus Z olefins for some pretty tricky alkenes. So let's look at this first example. So if we compare bromine and fluorine, which group is higher priority? Which group is higher priority? Bromine or fluorine? Bromine. So I'm going to put a number 1 here. Now let's look at our right-hand side. If we compare chlorine and hydrogen, what's higher priority? Chlorine or hydrogen? Chlorine. So is this a Z or E olefin? Z. Yep. Our high priority groups are on the same side. Okay, now let's think about naming this. We can either count 1, 2, so we'd have 1 bromo, 1 fluoro, 2 chloro, ethene. We don't have to say 1 ethene because if it's ethene, there's only one possible location for the alkene, right? There's only 2 carbons. Alternatively, we can name this as 2 bromo. Whoops, sorry. In the first name, I made a slight error. What goes first, fluoro or chloro? What goes first, F or C? What goes first, F or C? C. So I need to change this. So it would be 1 bromo, 2 chloro, 1 fluoroethene. In the second example, we have 2 bromo, 1 chloro, 2 fluoroethene. Okay. And which numbering method wins out? Red or blue? Which method wins out? Red. And the reason being, it gives the smallest possible locant numbers and it places the smallest locant number from each substituent, from first substituent to the last substituent, and it places the smallest locant number in alphabetical order. So this first naming convention wins out. So we'd call this Z, 1 bromo, 2 chloro, 1 fluoroethene. And you can even plug this in if you have Marvin Sketch on your computer at home. And the only reason why I say Marvin Sketch over ChemDraw is Marvin Sketch is free. But ChemDraw would work just as well. If you tell it to give you the structure to name, so structure to name, and we've named it perfectly correctly. So the name in red is 100% correct. Okay. Technically, you can name this as 1Z just to specify the olefin is at carbon 1, though it's a little redundant in this case, but if you're being thorough, you always put the locant number in front of your stereochemical information. Okay. Let's now just recap the following. So looking at this structure here, is the alkene E or Z? Is this alkene E or Z? So the structure that I've boxed, is it E or Z? Our high priority groups are on the same or opposite sides? They're on the same side. So this would be Z or 1Z, 1,2 dichloroethene. Looking at this next structure here are our substituents E or Z. Is this alkene an E alkene or a Z alkene? See a lot of responses of E. That's exactly right. So this would be 1E, 1,2-dichloroethene. Wonderful, wonderful. A lot of reasonable responses so far. So what I'd like you now to do is I'd like you to look at the following alkene and tell me whether it's E or Z. You do not have to name this one. We haven't covered the rules for naming this alkene just yet. But I want you to handle a more tricky example where you have to differentiate between an E and a Z alkene. And let's try to get a few responses in the chat. I see 2 responses so far. Let's get a few more. And it's okay if your responses disagree necessarily. Okay, so I see a bit of an even split between E and Z. So let's discuss. It's always good when there's not disagreement, but differing opinions. So let's start first and foremost with the left-hand side. So if we compare an ethyl group, so carbon to carbon, so it's a tie. So now we look at our next substituent. We're comparing hydrogen to carbon. So this ethyl group wins out. So this ethyl group is higher priority. Now, looking at our next substituent, so we have carbon to carbon. Well, that's a tie. Now we're comparing oxygen to carbon. So which group is higher priority, this alcohol or this isopropyl group? Which group is higher priority, the alcohol or the isopropyl group? The alcohol, right? Because oxygen is higher priority than carbon. So then, are our high priority groups on the same or opposite side? Is this Z or E? E. Yep, that's exactly right. So this is an E alkene. Perfect. Does that make sense so far? Is everyone comfortable with the idea of group priority and assigning group priority? And again, structure drawing tools are a great way to check your work. And in fact, if I punch this into the structure drawing tool, and you're welcome to punch it into Marvin's sketch if you have it, it designates the alkene as an E alkene. Wonderful. What about the bottom right? So we essentially split our alkene in half and we figure out the highest priority group on each side of the alkene. So we designated the ethyl group as higher priority on the left and the alcohol as higher priority on the right. Then we look and see whether they're on the same or opposite sides, or the same or opposite sides of your alkene. Yep. Perfect. Okay, so let's take a look at the following 2 alkenes, A or B. I'll give you about 3 to 4 minutes to work through these examples, and I'd like you to tell me for each of these alkenes, A and B, whether they're E or Z. And don't be shy to type it in the chat. You're more than welcome to break out the annotate feature and start writing priority numbers. Or you're more than welcome to use the annotate feature to write your proposed alkene stereochemistry. Whatever works for you. But I'd like to see a few responses and then we'll discuss in about 3 to 4 minutes. And if you have any questions, don't be shy to message me in the chat at this time. And just one piece of advice, count one atom at a time when assigning priority. Let's get a few more responses in the chat. And if anyone has any other responses, we'll discuss in a few more minutes. And we're seeing quite a spread of answers, but that's good, that's good. And don't be shy to revise your answer in light of further consideration. And we'll discuss in about 30 more seconds. I see a lot of responses in the chat, that's quite good. As we have almost the entire class has responded, let's discuss A first and foremost. So when assigning priority, you look an atom at a time. So if we compare this oxygen to carbon, what is higher priority, oxygen or carbon? Oxygen. Okay, now we'll do the exact same trick on the right-hand side. So carbon to carbon. Now attached to this carbon, let's make a table. We have 3 carbons and a hydrogen to this top carbon, and we have 2 carbons and 2 hydrogens on the bottom. So the top carbon wins out. So then, is alkene A, Z, or E? Are our high priority groups on the same or opposite sides? Are our high priority groups on the same or opposite sides? Is this Z or E? Z, exactly right. So this one, you just have to remember, when you're assigning priority, you go one atom at a time. So this alkene is Z. Okay, let's look at structure B, and that is a lot of different functional groups at play. So remember, we go one carbon at a time. So on this top substituent, we have 3 nitrogens and a carbon attached. On this bottom substituent, we have an oxygen, a carbon, and 2 hydrogens. What wins out, oxygen or nitrogen? What wins out, oxygen or nitrogen? Oxygen. So this bottom alcohol is higher priority. So a lot of these somewhat tricky alkene geometry questions are really testing your ability to assign priority groups in order of highest to lowest priority. Okay, so we are completely correct that the alcohol is higher priority. Let's now look to the right-hand side. So attached to each carbon, in this first case, we have 2 carbons, well, 3 carbons and a hydrogen, because this double bond counts as 2 carbons. In the bottom case, we have 4 carbons attached. So this T-butyl group wins out and is highest priority. So overall, is this olefin Z or E? Is this olefin Z or E? Are our highest priority groups on the same or opposite sides? See a lot of people typing Z. That's exactly right. Our highest priority groups are on the same side. Yep, perfect. Now that we've had a chance to see and attempt some problems and engage in the act of revision, let's take a look at one more example, and this will be our capstone example for this section. So take a moment and try to name the not name the following molecule, but just designate whether it's Z or E. We haven't covered alkynes just yet, but you do have enough tools to designate Z versus E for sure. So take a moment, take about 1 to 2 minutes, and you're more than welcome to type your responses in chat or using the annotate feature. So I see a lot of responses of E. Let's take a look at this example. So first and foremost, if we compare fluorine to carbon, fluorine's the clear winner. Now let's look at this next example. We have a carbon that's attached to 4 carbons versus a carbon that's attached to 2 carbons and 2 hydrogens. So what's higher priority, an ethyl group or an alkyne? What's higher priority, the ethyl group or the alkyne? The alkyne. So then, are high priority groups on the same or opposite face? The same or opposite side? Is this a Z or E system? Is this a Z or E alkene? It's E. Yep. And if you punch this into your structure drawing program, we get that this olefin, in fact, is E. Perfect. So far, so good. So the last thing that we need to discuss is EZ notation when you have multiple double bonds. So if you have more than one double bond, each one is analyzed and then declared to be E or Z. So in this case, we have 1E4Z, 1,5-dichloro, 1,4-hexadiene. So this is our carbon number 1. So we have an E olefin, and at carbon number 4, we have a Z olefin. So with that idea in mind, let's take a moment and let's try and name the following structure. We'll take about 2 to 3 minutes when naming this structure. And don't be shy to write or type the name in the chat, and we'll discuss in about 2 to 3 minutes. And don't be shy to type your proposed name in the chat, but we'll discuss in a few minutes. And since it's a diene, make sure to specify, just like in our example, the configuration at each of our alkenes. So I see a few reasonable responses. So let's entertain all of the available options. And let's start just first with our basic skeleton name. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So in blue, we'd have 3 bromo, 2 iodo. Remember, we write our substituents in alphabetical order. Hexa, 2, 4 diene. That's one option. Don't worry, we'll include stereochemistry after we resolve what the baseline name is. The other option would be 4 bromo, 5 iodo. I keep putting the dash after iodo. That's not necessary. So you have hexa, 2, 4 diene. So which numbering method is preferred, blue or red? So our alkene locant numbers are a tie. So now we resort to substituent locant numbers. And which method is preferred, blue or red? Blue, yep. Okay, perfect. So now we have the skeleton, 3 bromo, 2 iodo, hexa, 2, 4 diene. Okay, now we have to specify E versus Z. And for that, I'm going to clear out my blue and red numbers. And now we're just going to think in terms of priority. Okay, so I am going to include my locant numbers here, just so that way I don't get my olefins mixed up. Now, looking at alkene at carbon number 2, what is higher priority, iodine or carbon? Which group wins out, iodine or carbon? Iodine, okay, so we'll put a number 1. And what wins out, bromine or this alkene? What wins out, bromine or carbon? Bromine, okay. So then, at alkene at carbon number 2, is it E or Z? Is it E or Z? Is our olefin E or Z? E. Yep, exactly right. Okay, now let's look at our olefin that starts at carbon 4. Now, obviously, the hydrogen will be lower priority. So we can just circle this giant substituent. It'll be number 1, and the methyl will be number 1. In this case, our alkene at carbon number 4 are large substituents on the same or opposite side. Do we have a Z or E olefin? E, right? So it'd be 2E, 4E, 3 bromo, 2 iodo, hexa, 2, 4 diene. It's a mouthful. If you're curious on how computers represent structure, computers like to code every structure using something known as a Smiles number, depending on what program you're using, and that the computer can read instead of having to decipher IUPAC when spitting out the structure. If you type a correct IUPAC name into Google, you will see that structure as the first hit. But we are correct in noting both of our olefins are E olefins. Wonderful. Any questions on this example? So this is probably something that you may see on an exam if I wanted to test nomenclature, because it's a 2-for-1. It tests your numbering, it tests your stereochemistry. It's comprehensive. Any other questions before we move on to the next section in this chapter? Okay. So I'll let you save these next 2 examples to work on at home. You may see these again on the homework, so they'd be good to practice. Let's talk next about this idea of alkene stability. So cis alkenes are less stable than trans alkenes, and it has to do with steric congestion. If you have bulky substituents held in the same relative region of space, you have this steric repulsion, which destabilizes your molecule. Now, alkenes typically can't equilibrate under baseline thermal conditions, but if we have an acid catalyst, you can equilibrate between your alkene stereoisomers. Now, one way that we can measure the relative stability of alkenes is to compare the heat given off on hydrogenation. The less stable isomer is higher in energy and releases more heat. So the more stable alkene, by the corollary, gives off less heat during hydrogenation. Okay? So, as we notice, if we compare the trans and cis isomer, the cis isomer gives off a greater amount of heat. So cis gives off more heat during hydrogenation. The nice or slightly dangerous thing about hydrogenations is because they're exothermic processes, you can potentially, as the hydrogenation proceeds, your reaction mixture can increase in temperature and it can eventually run away if you aren't careful. Beyond that, does everyone see from this chart, and would someone like to, so if looking from this chart, we see the cis is higher energy, the trans isomer is lower energy. Is our product from hydrogenation of both of these alkenes the same? Are we making the same product in both cases? After hydrogenation, is the product the same? Yes. So we have the same product. So any difference in the heat of hydrogenation is due to a difference in the energy of our starting reactant. Just as an interesting quirk, since we're really good at reading reaction energy diagrams, which alkene would we expect to react faster? Which alkene would we expect to react faster? The trans, exactly. This is an exergonic reaction. And the trans starting material is lower in energy, and as a result, since our transition state resembles our reactants, we'd expect a lower activation energy for the trans isomers hydrogenation. That can be exploited later on in hydrogenation reactions. Anyway, the key takeaway from this discussion, cis alkenes higher in energy. Perfect. Okay, so if we look at the stability of alkenes, alkenes are stabilized by increasing substitution, and we'll invoke this idea of hyperconjugation once again. the more substituted our alkene is. So tetrasubstituted, we have 4 substituents. Tri would be 3, di would be 2, monosubstituted would be 1. And these are carbon, oxygen, nitrogen, hydrogen, carbon, oxygen, nitrogen, and halogen substituents, not hydrogen. So, and specifically when we refer to something as tetrasubstituted, we're looking at carbon substituents. And the reason why we care so much about the number of attached carbon substituents is that alkenes are stabilized by hyperconjugation. So electrons in a neighboring filled sigma bonding MO stabilize the vacant pi star orbital. This is a net positive stabilizing interaction. Okay, so we have our sigma bonding MO. It's overlapping with the pi star, and that leads to a stabilizing interaction. Similar to how our sigma bonding molecular orbital overlapped with the empty p orbital in a carbocation to stabilize that carbocation. Okay. So this act of hyperconjugation stabilizes our alkene. So hyperconjugation stabilizes the alkene pi bond. Yeah, so the more hyperconjugation we observe, the more adjacent carbon substituents, the more stable our alkene is as a result. So this is very familiar to what we've seen in previous discussions of hyperconjugation. Any questions before we move on from this idea? Any questions before we move on from this idea of alkene stability? The more carbon substituents we have attached to our alkene, the more stable our alkene will be. Does that make sense? Is everyone comfortable with this idea? Okay, perfect. So let's look at some reactions of alkenes. So the first of which is electrophilic addition. So electrophilic addition is where we have a nucleophilic pi bond, and we use that nucleophilic pi bond to form 2 new sigma bonds. So in electrophilic addition to our alkene, first and foremost, our alkene is protonated by forming a CH bond, and then the carbocation is attacked by the nucleophile. Okay, so we have our protonation step, followed by addition of our nucleophile. And we call this process hydrohalogenation. Hydrogen, halogenation, halogen. Perfect. Now, remember in our discussion of entropy and enthalpy, we noted that addition reactions are disfavored by entropy, and elimination is favored by entropy. So generally, addition reactions are run at low temperatures to avoid competing elimination. Okay, so most addition reactions that you'll see in the literature are run pretty cold, just to avoid accidentally eliminating your halogen. Okay, so let's look at the electrophilic addition energy path. So the first transition state is the high energy point. So as a result, the first step, which is alkene protonation to generate the carbocation, is going to be our rate limiting step. Does everyone see in the graph how our step with the highest activation energy is our first step, the protonation step, step 1. Does everyone see how step 1 has the largest activation energy? Yes, perfect. Okay. So our step one is the rate limiting step. After we generate our carbocation, the addition step is not rate limiting, it's relatively fast. One thing I want you to pay attention to is going from left to right on the reaction coordinate is addition. And if we go from right to left, this is the reaction coordinate for elimination. So as we can see from this graph, the rate limiting step for elimination is loss of our leaving group. So this is the delta G reverse for step one of elimination. Addition and elimination are two sides of the same coin, a forward and reverse reaction almost. Okay, perfect. So we've established alkene protonation to generate the carbocation is the rate limiting step. So with this idea in mind, we're going to look at a few electrophilic addition reactions, and we're going to try to determine some general trends in reactivity. So one thing we notice is that for electrophilic addition, we have choice of a primary versus tertiary carbon. And we notice overwhelmingly our halogen ends up at what carbon? The primary or the tertiary carbon? Our halogen ends up at what carbon? The tertiary carbon. Okay. So this is implying we're going through an intermediate with a carbocation at what carbon? Where is our carbocation going to be? Primary or tertiary? Where would our carbocation be? Primary or tertiary? Tertiary, exactly right. And that's how our halogen is adding to that carbon. Okay, so interesting observation. We notice a strong preference for the tertiary species. Okay. Let's look at the following example. This potassium iodide and phosphoric acid is just making hydroiodic acid. And we notice again, we have two carbons to choose from, primary or secondary. And we notice overwhelmingly what carbon is our halogen installed at? What carbon does our halogen end up at? Primary or secondary? Secondary, exactly right. And that implies we're going through an intermediate. 1, 2, 3, 4. 1, 2, 3, 4. Where we have a secondary carbocation that is then attacked by our halogen. The halogen adds to the location of our carbocation. Perfect. Okay, so we're beginning to establish some trends here. And from these observations, from product reactivity, before even the idea of a carbocationic intermediate was necessarily proposed, there was a general pattern of reactivity observed for these reactions. And we call these rules Markovnikov's rules. So for an asymmetrical or unsymmetrical alkene, HX reagents or halogen-derived acids can add in two different ways. But one way may be preferred over the other. So electrophilic addition of HX reagents is Regio selective, region selective, and follows Markovnikov's rule. Okay, so what does Markovnikov's rule state? The halogen is generally installed at the more substituted carbon. So think primary less than secondary, with tertiary being most preferred. Okay. The hydrogen is generally installed at the least substituted carbon. Okay. So as we can see, if we have a choice between a primary and a tertiary carbon. Let me do this in dark ink. So if we're comparing a primary and tertiary carbon, where will our halogen add if we're following Markovnikov's rule? The primary or the tertiary carbon? Where will the halogen end up? Primary or tertiary? What's the more substituted carbon? Primary or tertiary? Tertiary. Okay. So that's why our halogen ends up at the tertiary carbon. Perfect. Likewise, if we try halogenation of 1-methylcyclohexene, if we compare, we have a secondary carbon compared to a tertiary carbon. Where will our halogen end up invariably? Secondary or tertiary? Again, tertiary. It's the more substituted carbon. Now, this is strictly an empirically derived pattern of reactivity. We know from our background looking at the reaction coordinate, it's derived from this idea of carbocation stability. So let's take a look at a few cases where we just don't see much selectivity. So looking at 2-pentene, we have the choice between a secondary and a secondary carbon. Not much of a choice now, is there? Would we expect any selectivity? Is there any preference? Or are both of these products generated with relatively equal preference? Is there any distinguishing factor between these two secondary species, these two secondary carbons? Is there anything that differentiates them? No. And as a result, there is no selectivity, or no selectivity observed, or no substantial selectivity. No strong selectivity is observed. Now, I'm going to restate Markovnikov's rule in a way that will allow us to use it with a little bit more predictive power. So this isn't Markovnikov's rule one-to-one, but it's how we're going to be reasoning through a lot of these examples. So Markovnikov's rule, if I'm restating it, considering what we know about the reaction mechanism, the more highly substituted carbocation forms as an intermediate rather than the less highly substituted one. Perfect. So that explains why we see addition of our nucleophile at the more substituted carbon. Tertiary cations and associated transition states are more stable than primary cations. So this tert-butyl carbocation is more stable, ergo, that's why we see the chloride add at the tertiary carbon. And all is right with the world. Everything's making sense so far. Okay, now let's keep going. Let's look at a few more examples and let's see. If I were to restate Markovnikov's rule one more time in order to use it for a range of examples that we'll see in this next chapter, the more stable carbocation forms as an intermediate rather than the less stable carbocation. And the reason why I restated in this manner is we're going to begin to look at examples where we aren't just able to make a call based on primary, secondary, and tertiary. We have to consider a few other factors. So our nucleophile is going to add at our carbocation site. So let's review and let's discuss carbocation stability to make sure we're considering all the factors that we need to. So first and foremost, adjacent alkyl groups stabilize carbocations. That's where we see this trend where tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl carbocations. Now, adjacent carbon-carbon pi bonds stabilize carbocations via resonance. So you have to be on the lookout for conjugated or allylic and benzylic carbocations. So for example, in cases where you can generate an allylic or benzylic carbocation, these processes are especially favorable because allylic and benzylic carbocations are especially stable. So this carbocation would be benzylic, and it's stabilized via conjugation to this aromatic ring. Okay, so let's try to next answer the question, why does electrophilic addition follow Markovnikov's rule? So why does this rule hold up? Well, we know from the Hammond postulate, the transition states for endergonic steps resemble the products, and the transition states for exergonic steps resemble the reactants. And the transition state should be similar to an intermediate reactant or product that is close in energy to the transition. Okay, so we have our endergonic and exergonic reactions. Let's now look at electrophilic addition. Let's look at electrophilic addition. So, just to show each of the steps, first we have protonation. That's step 1, and in step 2, we have addition. If a reaction occurs in more than one step, it must involve species that are neither the reactant nor the product, and we call these species intermediates. So our intermediate is our carbocation. So looking at our reaction in step 1. Step 1 is our rate limiting step. So step 1. So step number 1, would we consider step 1, looking at this chart, is step 1 exergonic or endergonic? Is our delta G for the first step greater than or less than 0? Is this endergonic or exergonic? The first step. The first step is endergonic. Exactly right. The delta G is greater than 0. Ergo, our transition state is going to resemble what? The transition state is going to resemble our reactants or products. Resemble our product intermediate carbocation. I'm going to put products in quotes in this case. Okay, so our intermediate and transition state are going to resemble each other. So they're going to look very carbocation-like. Okay, perfect. So we've established that from our first look. Let's keep going now. Now we're going to compare, and we're going to take a look for the first step. So we've established from our previous discussion, so step number 1, which is protonation, is endergonic, rate limiting, and the transition state resembles the carbocation intermediate. Right? That's what we've established from our previous discussion. So let's compare, and let's compare our two reaction pathways. And these should look very similar to you. Pathway A and pathway B. So in pathway B, we have a tertiary carbocation. In pathway A, we have a primary carbocation. So by comparison, what is lower in energy? A tertiary or a primary carbocation? What is more stable? A tertiary or primary carbocation? Tertiary. So we have a more stable carbocation, and as a result, would our transition state be higher or lower in energy? Would our transition state be higher or lower in energy? Lower. A low energy intermediate, our transition state resembles that intermediate, ergo our transition state is lower in energy. Okay. So in summary, for the following endergonic reaction, so we established our transition state resembles the products. If the transition state is lower in energy, the activation energy is lower, and in turn, the reaction's faster. Rate limiting simply means, so this first step is the slowest step in our chemical reaction. And as a result, the rate limiting step controls the rate of reaction. So it's the slowest, it's the step in a reaction that limits production of product. So this is the slowest step with the highest activation energy, and in turn, any steps after the rate limiting step do not contribute substantially to controlling the rate of product generation. So rate limiting is essentially the step that controls the rate of reaction. Perfect. Thus, what we can conclude from this picture comparing the two reaction pathways for a primary and tertiary carbocation is that the reaction that produces the more stable carbocation occurs at a faster rate, and that in turn favors our tertiary carbocation derived product. Does this idea make sense? From our analysis of the following reaction energy diagram, does it make sense that we came to the conclusion that the tertiary carbocation intermediate is generated more readily, has a faster rate of generation, and as a result, in our products, we'd see more of the products with our halogen at the tertiary position? Does this make sense to everyone? Any questions? If you increase the temperature, you see another entirely different pathway prop up. Temperature control more has an influence if your substituents are allowed to, or if your species are allowed to equilibrate. Temperature doesn't have a dramatic effect on Regio selectivity in this case. Does that make sense? Does that address your question about how temperature could affect the selectivity? Temperature doesn't play a substantial role in this case of controlling selectivity, because the difference in energy between a primary and tertiary carbocation is substantial. If you do change the temperature, you'd probably see elimination pathways start to prop up or other side reactions. Does that make sense? Perfect. Okay. So let's take a look now at the following energy diagram. So we're looking at electrophilic hydrobromination of an alkene. Let me zoom in. And we've seen this energy diagram before. In terms of mechanism, we have our protonation, followed by addition to generate our product. We've established that the bromine prefers to add at the tertiary carbon, as that's the site that has the most stable carbocation, which is generated most readily in the rate limiting step. So just to highlight this, the reaction that produces the more stable carbocation occurs at a faster rate, favoring the tertiary carbocation product. Okay, so now let's discuss and let's really break down this idea of where a carbocation transition state came about. What evidence do we have for a carbocation transition state, or a carbocation-like transition state and a carbocation intermediate. So to support this idea of carbocationic intermediates, we've observed a range of carbocation shifts. So carbocations can undergo structural rearrangements, such as 1,2 hydride and 1,2 alkyl shifts to give the most stable carbocation. So in this case, we observe chlorination at both the secondary position and a tertiary position. Notice how our alkene is not at both sites of chlorination. So after protonation to generate the secondary carbocation, we observe, or we propose, or we suspect that there is a hydride shift to generate a tertiary carbocation, which is more stable, lower in energy, and then and only then do we see addition of our halogen to the tertiary carbocation. This is why we see a mixture of Regio isomers. Another example that provides evidence for a carbocation-like intermediate is that multiple Regio isomers, we can see multiple Regio isomers for delocalized or conjugated carbocations. So for example, after protonation, we have multiple potential sites that have cationic character. So this first carbon has a positive charge as well as this second carbon. And we can observe addition of our nucleophile to both cationic sites. That's why we see a mixture of Regio isomers. As our carbocation is conjugated, and this positive charge can be delocalized throughout our molecule via resonance. So we have multiple sites that are carbocation-like and multiple sites where our nucleophile can add. Does this make sense to everyone so far? Okay, perfect. So let's keep going then. And let's start off first with a simple premise. Let's try to draw the major product for the following reaction. Let's try to draw the major product from this reaction. So don't be shy to break out the annotate tool, or you can send a link to a screenshot of a structure you've drawn, or you can provide the name. So let's get a few responses either in the chat or using the annotate feature for the major product from this reaction. So this first reaction. This is a textbook hydrohalogenation. And let's try to get a few more responses for the proposed major product after hydrohalogenation, and then we'll discuss in about a minute. And remember, nucleophile addition occurs after carbocation generation at the most stable carbocation site. Yep, looks perfect. Perfect. So let's now discuss, and I'll provide my instructor solution. So mechanistically, I always like to think about things from the perspective of mechanism arrow pushing. First things first, our alkene attacks and gets protonated. We generate our carbocation intermediate. Our halogen then attacks at the carbocation site. We generate the tertiary carbocation preferentially, as it's the most stable, lowest energy carbocation, and it's generated most readily under the reaction conditions. And that in turn generates the following halogen. Just as a side note, since it goes through a carbocation, we have a mixture of stereoisomers. Which doesn't matter in this case because this compound's meso, it's symmetrical. So it's a moot point regardless, but I just want you to note that carbocations are flat, so they can react from either face, so you get a mixture of stereoisomers. For this compound, it doesn't matter as much since it's symmetrical, it's meso, but for later compounds, I just want to make sure that you indicate very clearly you make a mixture of stereoisomers. Does that point make sense to everyone? Carbocations are flat, so you can attack from the top or the bottom. Okay, let's now try to tackle a very interesting case. Hint, think about shifts that may occur, and I'd like you to draw a mechanism for the following reaction. No, it's not a typo. The bromine does end up on that carbon. So let's give this a few minutes. Let's spend about 3 to 4 minutes. You're welcome to break out the annotate feature and try drawing a mechanism for this reaction, and then we'll discuss in a few minutes. Yep, looks good so far. Yep, you generate the carbocation. The carbocation shift is drawn. And what intermediate do you now generate? Yep. And then the halogen attacks. Exactly right. Perfect. Perfect. Wonderful. So allow me to just clear this and then I'll write the instructor's solution so that way we have it all in the note set. But that was perfect. Yep, so in our first step, we protonate our alkene and we generate preferentially the secondary carbocation. Next, we have a hydride shift to generate our tertiary carbocation, followed by attack of our halogen to generate our alkyl bromide product. Pretty cool reaction. And if you're really creative with manipulating your substrate, you can get some really interesting hydride and alkyl shifts. Does this example make sense to everyone? We've seen alkyl and hydride shifts in the previous chapter, and now we're just combining it with a new reaction mechanism. Okay, let's keep going. So now that we've had a chance for revision, let's attempt these next two examples. Let's try drawing the major product for this first reaction, and let's try drawing a mechanism for this second reaction. And just as a correction for this second reaction, without the olefin. So your second reaction product would be lacking the alkene. Just clear that out. And you're more than welcome to break out the annotate feature or write the name of the compound in chat or follow along on a separate sheet of paper. And we'll discuss in a few minutes. And don't be shy to break out the annotate feature and propose a solution to each of these two problems. the first product is exactly right. The first product proposed is spot on. So allow me to clear, and then we'll discuss this mechanism. So you're exactly right. In the first step, we protonate our alkene to preferentially generate the tertiary carbocation. And then the halogen attacks your tertiary carbocation to generate the tertiary alkyl bromide. Perfect. Would someone like to propose now a mechanism for the following reaction using the annotate tool? Take a few moments. I apologize for the typo. The reason why I changed this example is this product is a little bit tricky right now. We haven't yet covered the elimination type reactions yet. So we'll stick with this first example. Yep, first step, protonation, exactly right. Yep. Yep, followed by a hydride shift. And then addition. Yep, spot on, exactly right. So allow me to clear annotations, and then we'll just provide the instructor solution. And this will be the last example for today's class session. So we protonate our alkene, and we generate preferentially our tertiary carbocation. We have a carbocation shift. Followed by addition of our halogen to yield our tertiary alkyl chloride. Perfect. So this is a good stopping point for today. We'll continue on with this chapter next class session. We're on track to finish this chapter by next class laboratory.